Okay, welcome everyone to this evening's Timber Development UK Southside Hereford University Design Challenge 2022 webinar in partnership with Passivhaus, Edinburgh Napier University and NMITE, and of course thank you also to our sponsors that are listed across the bottom of the screen. So just a very brief overview of the design comp. It's based upon a Stronger Towns project, which is in Southside Hereford, so it has a budget of 1.6 million. It's looking at the development of a community focal point in the South Y area, the space of which will be circa 800 metres squared rather, is to provide a community for the stakeholders that will enhance the local biodiversity, regenerate lives of the people that own, use and visit. And it's climate ready and cause minimum impact to the site and planet. And of course, it should be predominantly made from timber. So this gives you a sort of visualization of the project, but of course, this is purely a conceptual design that's been used for promotional purposes, showing the main stakeholders and the position of the project. And it's to bring this collective of stakeholders together as well as the community. But please, of course, when you're working on your design and indeed the challenge, it's very much a blank canvas and how you can respond to the client brief. So with respect to the challenge itself, it's not just a challenge, it's backed up by a webinar series and a whole bundle of information. So we'll post these links in the chat so you can access this. You can go to the YouTube channel and view the previous webinars if you haven't seen them, or replay this one. And there's also further information available. And of course, if you haven't done so already, then you can go and to Eventbrite and book on to the future ones. So with that brief introduction, we'll move on to the main event of this evening. And I'll hand over to Kelly Harrison of Whitby Wood, who will just give a brief intro to the evening and to the speakers. So Kelly, with that, I'll hand to you.
Thank you very much, Robert, and hello everybody. It's very exciting to be here and a really interesting evening of talks lined up here. So hi everyone, I'm Kelly Harrison. I'm a structural engineer, associate director at Whitby Wood, but also I sit on the board of directors for Timber Development UK and get quite involved with some other speakers here as well in the sort of university engagement and the sustainability circular economy committees that we have. So it's a really exciting time for timber, and we've really got a great lineup this evening. So I'll just give you a little intro to each of our speakers, and then we can get right into the talks and business. So first up, we've got Matthew Caldwell from BuroHappold. Matt's an associate structural engineer based in BuroHappold's Bath office. He graduated with first-class honours master's degree in civil and architectural engineering from the University in Bath in 2004. Since then, he's worked on a huge range of projects and structures around the world, ranging in scale from developments in hundreds of millions of pounds of Premier League stadia, all the way down to bespoke residential dwellings, footbridges, and artist installations. Matt's part of a small team within BuroHappold's global engineering community, which promotes and builds the company's expertise in timber design. And thank you very much for joining us this evening, Matthew. You're going to be talking about optioneering your materials and minimizing your impact, which is great. We'll then go on to Abel Munoz. So Abel is a technical manager at James Jones & Sons Limited and their Timber Systems division. Abel has been technical manager for James Jones & Sons since 2003, where he's involved with the specification design of OSB webbed timber I-Joists or JJI joists in floors, roofs and walls. Abel holds a degree in forestry engineering, very interesting, a postgraduate diploma in technology management and a master's in timber engineering. He is currently undertaking a PhD in timber engineering at Edinburgh Napier University, researching the vibration behaviour of timber floors built with timber I-Joists in UK residential dwellings. Abel's interests include computational analysis of timber I-Joist structures, serviceability behaviour of timber floors, and life cycle assessment of timber products. You're very well qualified, Abel, and I think I can learn a lot from you, so I'm looking forward to your talk. Then we have James Norman looking at solid sections. So James is a professor of sustainable design and civil engineering at the University of Bristol. He's got 16 years teaching experience and 12 years industry experience. James is a creative educator, which I hope we'll see a little bit of tonight as well, and has been awarded the National Teaching Fellowship. James loves teaching as a timber enthusiast. He teaches all aspects of design from concrete to rammed earth, as well as being involved in a third-year research project and final year design projects. Recently authored Designing Timber Structures, an introduction for TRADA. Structural timber elements are pre-scheme design for TRADA, which is one of the most useful books we have as structural engineers, and a conceptual design of buildings for the I-Struct. Thank you very much for joining us, James. And we also have Beth joining us today, which is very exciting. So Beth graduated from the University of Sheffield in 2011, and she studied structural engineering and architecture. Beth has worked in architectural and engineering practices in Sheffield, Gloucester, and now Bristol, working on projects from domestic extensions to new build sports halls and high security NHS facilities. Now a chartered engineer, Beth specialises in timber engineering and low energy construction. Beth is a certified passive house designer, a local group leader for the AECB, and is passionate about making low energy carbon building available to all. I mean, Beth is one of the few structural passive house designers out there. So yeah, it's great that you're here, Beth, and we can't wait to hear about all the inventive details you've been having to get up to. So I will now pass over to Matthew to start the talk. Thank you.
Thanks, Kelly. I'll just share my screen. Okay, hopefully that's popped up for everyone there. Yeah, thanks very much for the introduction. As Kelly said, I'm a structural engineer, so what I'll be talking about will mainly coming from that point of view, but obviously there's a lot more to the building than that, I acknowledge. Okay, a bit of a backdrop. I'm going to use the word carbon at least, well, probably every couple of minutes during this talk, and just so that we understand what I mean when we're saying that, we usually use the word carbon to mean carbon dioxide equivalent, which is really just a sort of common denominator that we're using to measure the global warming potential of a material or a process or a combination of them. So every time I say carbon, please take that as meaning just a measure of the global warming potential of a thing or a system. And this probably, I'm sure everyone who's presented has probably talked about this to some extent, but the backdrop to where we are, we've had the Paris Climate Agreement and then COP26 quite recently. To coordinate with COP26, the government released this net zero strategy document. And it's quite a large document, but if you do delve into it, there are some useful clauses in there. 50 there you can see is sort of acknowledging that using different materials is a important part of the picture. And then further on, earlier in the document, it talks about timber specifically and the way that the government is looking to acknowledge and promote the use of that. Now we know what carbon is. Just looking now about the carbon within a building, there are many ways that we're creating sort of global warming potential with a building. Just sort of splitting it bluntly into two compartments is the embodied carbon of the materials and the operational carbon of running the building. Now, the embodied carbon of the materials is something which you kind of spend all that carbon right at the start, or the vast majority right at the start. And obviously right now is the time when we need to be reducing our emissions. Over the life of the building, the operational carbon may go down, hopefully it will, as the grid decarbonizes, and potentially pieces of plant or equipment within the building might be more efficient. So over time, the proportion of the carbon footprint of that building will go, the proportion that's embodied carbon will get larger and larger over time. So it just emphasizes the importance of us considering that now. It's important today, and it will continue to be even more important over the life of the building. Then just breaking it down, looking specifically at the structure of a building, and just getting a handle. This is a study that we did. It's actually for an office building, but the general principles will hold for any building really. In looking at where the sort of heaviest amount of carbon is in the building, and you can see that a huge amount of it is in the floor slabs or the construction of the floors. So that's definitely an area to put focus on. This study, the assumptions on the foundations had to be quite sort of generalized because that varies an awful amount between sites. That amount in the foundations can also be very large, especially if you've got deep piled foundations, if you've got poor soil, for example. But yeah, bearing in mind that the floors is somewhere to really focus your attention. If you're looking at sort of columns, you can see there, you know, swapping materials or spending a lot of work on them often is not as beneficial as focusing your attention on the floors. And then while we're talking about embodied carbon, you obviously want to get a handle on what you're aiming for and what you've got within your building. This is a kind of fridge magnet type measurement, I suppose. This is pulling out figures just for the structure itself. So this is used, those sources on the left there, to kind of boil it down to just the structure. Obviously the REBA targets would include the building as a whole. But when you do your analyses, you count your carbon, you can see where you are on this chart. Obviously the higher up the better, and we should certainly be trying to get into the 350 territory and you know, aiming higher and higher up into the lower figures above that. As you go through your project, you will make different decisions at different stages in your project, and you'll see from this chart here, which is reproduced in various forms all over the place, the story it's telling here is basically you've got the most potential to have a positive influence right at the start of the project. So at the start of the project, you could be deciding materials overall. You could be looking at whether you're building 10 stories or 5 stories, whether it's a tall building or a wide building, if you like, whether it's framed or whether it's load-bearing walls, and also controlling the grid. And as the project develops and the design develops, you'll have less and less ability to influence it. So making the big decisions in an informed way early on is extremely important. And sort of digging into that a little bit further, the optimizing the grid is extremely important, and different materials will suit different grids in different ways. There's often pressure, especially with an office building, to have very large grids, but you really need to sort of question whether that's necessary. You can see on the left there, this is just some studies that we did of reducing the grid size for 3 different sort of basic construction types there. You can see with concrete, you can make a huge saving by reducing the grid down. Less so with timber, but then it was a lower embodied carbon in the first place. And then on the right hand side, you can see a sort of plot of the benefits in embodied carbon as you reduce the spans there, sort of going down from the sort of 9.5 meters down to 7.5. You can see a benefit. Obviously, it needs to be balanced with what the spaces need to do within the building and the architecture of the building. Once you get down to really short spans, you're seeing less benefit in embodied carbon terms, but also you need the building to sort of function over its lifetime, obviously. And dare I say it, a wholly timber structure is not always the best answer. That you need to use timber in an appropriate way, rather than shoehorning it into a design which doesn't suit it. There may be elements within a structure where you have lower embodied carbon and a more efficient structure by introducing another material. The other way of looking at it is if timber is coming out as a very inefficient way of forming a particular element, then maybe you need to go back and look at the way that the structure is framed, where the loads are going, and sort of revisit it that way around. But it's not always most efficient to have timber everywhere. Don't force it to do things that it doesn't do efficiently. Another important part with any material is considering the whole life of that material. What we don't want to do is to only consider putting it up on day one and not really thinking about what happens to it during its life and at end of life. And with the carbon counting modules there, you can see that you need to get any benefit out of things, you need to consider the later modules as you move across the diagram. And particularly with timber, one of the huge advantages of timber is the carbon that it stores while it's been taken out of the forest, but it hasn't yet been burnt or disposed of. And the benefits of that really only come about if it's a long-lived product or series of products. What you don't want to do is to have something which is used for 20 years and then burnt, or even worse, taken to landfill. So considering the way that your elements are designed individually, and particularly the way they're joined together within your building, will decide whether you can take the whole building down and rebuild it somewhere else, whether you can adapt your building in situ, whether you can take the elements apart and put them into a new structure. So considering that is very important, and particularly so with timber. This is a big debate, and one that's had on a regular basis. The word sequestration is used a lot. I prefer to use the word storage. It's not worth trying to understand this whole diagram below here. It's probably just worth saying that it is complicated. There's a lot of carbon going in and out of a project, and you will see projects in the architectural press which claim to be either carbon neutral or even carbon negative. And when you read that, you just need to look into it carefully and understand what the claim is precisely. Depending on how you run your numbers, if you use all the sequestration figures for timber, your analysis could indicate that putting more timber in is better than less. And the more you put in, the better it performs in terms of it being a negative value, which obviously doesn't make sense. You don't want to make a beam twice as big as it needs to be. Those numbers are not really telling the story. So yeah, I like to quote the stored carbon within a building rather than calling it sequestered. And we talked a lot about the superstructure, which is normally where you focus a lot of your attention, probably because it's the bit that you see, and that is the bit which is most readily, I suppose, changed between materials. But it's worth keeping in mind the substructure. So the sort of the default material for substructures is obviously concrete, and there are good reasons for that. It's durability, but it's worth considering other options. So particularly in the Netherlands, they use a lot of driven timber piles, and there are certain considerations that you need to have with that around durability primarily, and it will depend on your soils whether that's relevant, and also where the water table is. Otherwise, you might end up having to have a reinforced concrete cap on the timber to go down to the water table anyway, and it might not be practical. Helical screw piles are a good option for, particularly for lighter buildings. So your scheme here is 1 to 1.5 stories. This could be a very possible solution. It does depend on the soil to some extent. But the advantage of these is that there's far less material used than there would be in a a concrete pile, and it is removable, so facilitating that circularity again. You know, in principle, at the end of the building's life where it is, you can take them out and reuse them. Often also you can get the option of the central pipe, if you like, which is forming that pile, can be used can be reusing usually excess stock from the oil industry, which is quite a nice sort of poetic side of it. There are obviously advantages in that going into a product rather than going to be recycled per se. And then if you do end up with piled foundations, you don't have to default to a big lump of concrete pile cap. Think about precast or steel. Again, those can facilitate circularity and reuse of the elements, either as an assembly or individually. And do the math. Have a look at what you're using within the building, and especially if you're optioneering, even if it's quite rough, you don't need to have it down to the very last kilogram. Even just making rough estimates early on, it's much better to have a rough analysis to help you inform your decisions rather than waiting till the end to get a sort of perfect one. And these are just some examples of sort of studies we've done of sort of what material you need to do a certain job, and switching between different material options within a construction. And sometimes your gut instinct isn't quite right. This is just an example of a concrete structure, which I just ran quickly, so maybe don't quote it directly, but you would possibly instinctively think the hollow core plank is going to be low embodied carbon because it's you know, pre-stressed and it's got fresh air inside it, so it's not just a solid lump of concrete. But actually, when you dig into it, you often find that precast concrete manufacturers don't want to use any cement replacement, so they want to cast it to cure as quickly as possible, get it out the door, off their production line and sold, which means that you're probably not getting any cement replacement in it. So the material itself is actually quite carbon dense. Whereas you might think an in situ poured slab would be higher embodied carbon, and it certainly would be if you were using no cement replacement. But if you can, the advantage of in situ is that you can then introduce cement replacement. And if you went to very high levels of GGBS, like sort of 70%, that could come out, even though there's more material, it could come out lower embodied carbon than the precast plank. It's obviously not as good for DFMA and sort of modern methods of construction, and it's not as good potentially for circularity. But I suppose the point is just to look into these things and consider the detail of it, because sometimes your gut reaction isn't the whole story. And just to talk about timber specifically, you probably have presentations already on this, but the advantage of engineered timber that we have available to us now, which didn't have sort of 50 years ago. Traditionally, if you needed to make a big beam or a big column, a large section of timber, you had to find a tree that was big enough to have that bit of timber effectively inside it. It would have been growing a long time, and you wouldn't get all that much material out of that tree. You also then have got all the knots and faults which are in the timber, which means that you've got to sort of design according to that and cater for the fact that there could be a big fault right where you don't want it. Whereas nowadays we can make really big beams, as you can see there, but they're actually made out of lots of small pieces of tree, which means that you can use more of the tree. You can use trees which are not as old, and then by laminating it all together, we've also got a very consistent material there, so you're not having to cater for the fact that there might be a knot like all the way through the worst area of it. Then digging into timber a little bit further, or engineered timber, there's obviously lots of different forms of engineered timber, which are better or worse for certain jobs, and so you can get an efficiency in your embodied carbon and your cost and amount of material in general, just by selecting the right product for the right location. So you might look, if you were really trying to work some beams really hard, you might look at LVL instead of glulam. You might find that cross-laminated timber was becoming a bit inefficient for a slab, so you might go to I-Joists with plywood on top of it, for example. So it's worth looking, even once you've decided perhaps that you want a timber structure, looking at the different options of timber products within that. And they all have their associated embodied carbon. They've had different amounts of processing, transport, and there's some example numbers there. So just applying this to a project or an example project, then the sort of business as usual kind of dumb way of looking at it might be just to chuck in some reinforced concrete piles, because you kind of know that will do the job in most situations, and then cap that off with a big lump of concrete as a pile cap. And then you might put a frame in so that the structure is kind of separate to everything else in the building. And by doing that, you'll end up with you'll end up with point loads, which might need piled foundations. And then again, you might just pour, your slabs just in situ concrete, because that's kind of a bit of a default. You might just have your spaces on different stories of the building not stacked at all, so you're having to transfer out the weight of partitions above. Your partitions, again, you might just sort of go for concrete block, because that's kind of cheap and basic. And then brick facades are quite often used just to get, mainly to get through planning in lots of cases, and a roof void up there, which isn't doing anything for you. But then, looking at it in a bit more of a smart way, if it's a small building, you might look at distributing your loads to the foundation so that shallow strips or a raft works for you. That will reduce the amount of concrete. If you use load-bearing walls, you could be effectively forming some of the kind of architectural skin of the building and using that as a structure at the same time, rather than doubling up with a frame. And that will also help to distribute your loads. Stacking spaces so that you can have load-bearing walls. So if you've got a corridor or a partition upstairs, try and keep the same alignment downstairs. Keep the partitions light, because particularly if they're being carried on a slab or a beam without another wall below it. Lightweight facades do you need to pile up bricks to form your facade? And then perhaps a raft isn't working for you on your site for whatever reason. As I mentioned earlier, the helical piles, you can get reasonable capacity out of them. That allows you to remove them at the end of the job on its low amount of material. And you, instead of defaulting to a concrete ground floor slab, perhaps you pull the whole building up out of the ground, and that releases you to be able to do a timber ground floor slab. So sort of questioning what your instinctive assumptions might be about what form a building takes. And just to wrap it all up, really, be innovative, sort of push the limits, particularly with a competition like this. It might be that you've got in mind a product, and maybe it's not quite there in the market yet, but maybe you can push the limits a bit and invent it. This is an example product where they've used hemp all through the building, and it's a great example of sort of pushing things to the limit in material terms. There's a few links there, but I'm sure if you've not seen it already, you'll find it easily on the internet. But yeah, good luck, and try to push the limits and test yourself and the project.
Excellent. Thanks very much, man. That was really insightful. And I think what you've captured there is really how the modern structural engineering has to think, right? In terms of it's about how we structurally engineer for the future, and think about the materials that we're using and the optimization of those materials relative to the end use. And I think what was interesting as well is that the point about we want timber-based solutions, but we have to think also about the timber products we're utilizing within that end system, because they have different associated carbon credentials, etc. So there's that piece, and then also from the to the foundations in terms of not just the way of the structure, but how you set the structure out and the impact that has on the foundations. Indeed, the type of foundation that you can therefore specify, and there's a range of those. Yeah. So really, really, really useful. There was some comment in the chat, and the one that we probably missed out on is, I think your house is meant to be something of grand designs, or is that correct?
Oh, what you mean my background? Yeah, unfortunately it's not real. I wish it was. Yeah, it's borrowed from one of the architectural websites. So
I see.
Yeah, I like the look of it, but
I thought somebody had the inside track on you, and you had
I wish it was. I wish it was. I have.
No worries. Okay with that, but we'll have plenty of time for questions at the end as well, hopefully. So please pop your questions in the chat. We'll move on to Abel now. Abel Munoz, are you able to become live and share your screen? I obviously know Abel quite well because he's currently doing a PhD part-time PhD at Edinburgh Napier. And he's got a wealth of experience in terms of timber beam design and I-Joist. So with that, Abel, I'll hand it over to yourself.
Thank you. Thank you, Robert. Well, I hope you know me since you are one of my supervisors. Yeah. I was going to say, well, I can share my camera, but I'm afraid it's not that excited as Matthew. If I find it. Okay, guys. Thank you for inviting me to the seminar. I'm going to make a very short presentation about timber I-Joist and the structural principles justifying an I-shape design in comparison to the traditional solid rectangular section. First, let me introduce you to the timber I-Joist. A timber I-Joist is an engineered wood product which combines different products to form an efficient I-shape. The section at the edges, we call them flange material, whereas the element joining these flanges is called web. The idea of an I-shape is not really a new one. It was already invented in the 19th century by the steel manufacturing industry. However, it was not until 1969 that glue technology evolved enough for us to be able to manufacture such a product. And at the beginning, this product was a very bespoke one. They had timber flanges, finger jointed timber flanges, plywood webs, and their advantage was that it could produce very long span joists that at the time was seen as a desirable feature by some people who wanted very, very long open spaces. So very, very bespoke product. It gained some market, a rapid market expansion in the 90s. And the basic reasons due to this desire for large open spaces for another sector of society, but as well as mainly lack of availability of large timber sections in the US. And they also had some problems with imports. And some what the builders perceived lack of quality on some timber. So since then, I-Joist in the US propelled to become leader in the late 90s. Obviously, these companies have been exporting this product to the UK for a long time. And in 1999, James Jones, my company, who is one of the largest sawmilling companies, saw how this product was threatening their market share. So they decided to make a manufacturing facility the north of Scotland. And since then, it's been a story of gaining market share, basically in the mass volume UK housing. And one of the things that I see nowadays is how these products are very quickly replacing other materials in uses such as roofs and walls. Obviously, understanding the background or why an I-Joist section is really a good idea. Requires to understand different concepts and relating to internal forces and stresses within a timber beam. I only aim to do a very quick introduction to this concept. There are other resources available. So basically, when a beam is subjected to a load, that load is creating internal bending moments and shear forces. The bending moment can be seen as a torque that needs to be resisted by the beam. And this torque creates internal compression forces at the top of the beam and tension forces at the bottom of the beam. The transition that you can see between the compression and tension area is what in engineering we call the neutral axis. Lots of the beams also create what we call shear forces, that they are forces that threat to cut the beam in a similar manner as a scissor will do to paper if you don't have enough resistance in your section that can oppose to such forces. The magnitude of both bending moment and shear forces will vary along the beam. However, due to the nature of, this variation is due to the nature of the forces, such as a point load or a uniformly distributed load, or the fact that it is simply supported or a multi-span. For example, if you got a uniformly distributed load, you can find that your maximum shear forces will be near to the support and your maximum bending moments will be at the mid-span of the support. However, the cross-section of the beam at this stage will not influence the magnitude of these forces. Once we consider a section within a beam, these internal forces will become what we call stresses. Basically, a load over an area is a stress. And then we can talk about bending and we can talk about shear stresses. The magnitude of this stress is important because we need to ensure that they are not over a certain value or they are not over your strength values. Otherwise, you are risking failure in the beam. The distribution of such stresses without the cross-section can be determined using a formula that has been deeply ingrained in engineers' education. These equations are interesting in the fact that it tells us that the distribution of stresses within a section is dependent, the shape has an influence over the magnitude. For example, in bending stresses, you can see they are an I, which means the inertia, or inertia is the resistance of the beam to rotate. You can see that Y, which is the distance between the neutral axis and the fiber we are talking about. For the shear stresses, you can see the Q, which is the first moment of inertia, or a measure of how the area is distributed around the neutral axis. And a T will be your thickness, and again, your inertia, and M and V are your moment and your bending. Parameters such as inertia and the first moment of area, Q, will tell you that they are specific to certain shapes, and that's where your I or your square section can influence the results. As you can see, I have displayed here those formulas for a simple rectangular section. However, you can see certain trends when you're looking into these formulas, such as for bending stresses, for a certain shape, your moment and your inertia will be constant. So really, the distribution of the bending stress along the section, across the section, is dependent on the value of the y. So if your y is maximum, then you will have the maximum bending stresses. And that happens at the stream fibers, when y is equal to half of the depth of the beam. So quickly you can see that there is a conclusion that you can make in saying that maximum bending stresses will be always placed at the outer edges and the stream fibers, whereas they will be minimal or zero at the neutral axis. Similarly, when you're looking into shear stresses, you can see that the term V, which is the shear over the inertia and the thickness, is as well constant. So the shear stress really behaves in the same manner as the first moment of area. And that is maximum at the neutral axis and is always minimum of the stream fibers. So in essence, you can see that, you can see that if you had the choice to get a beam where you can make any material that you want and any shape that you want, what you really would like to do is to place your material with the highest bending strength at the stream fibers. And you also would like to put that material with the higher shear strength at the midsection in order to resist those stresses. And since in timber we've got, for example, very thin wood panels that have very good shear resistance, the shape of an eye seems to be ideal. So, as I said before, most I-Joist manufacturers will put a softwood flange at these locations. The main reason is because timber has a very good bending strength. Some manufacturers have replaced that with laminated vinyl lumber, LVL. At the beginning, as I said, the web used to be plywood, which it has been changed to OSB because OSB have a higher shear strength than plywood. Different manufacturers have different products. They usually have different depths and they will have different width for your flange. And they will play with these parameters to gain advantage on bending strength and shear strength and stiffness as well. One of the areas that we have talked when we talk about timber design is strength is an important property, of course, but most design in the UK, especially for UK floors, they are stiffness limited. I mean, if you look at the design codes, they normally reach deflection limits or vibrational limits well before that strength limit. So it's important to see how an I-Joist section can help to achieve a higher stiffness so that you can achieve the spans in actual design that you need. And looking, for example, a normal 220 by 47 all style C16 that used to be used in timber floors, and we will call that stiffness 100%. If we cut a portion from the middle, we have a 21% reduction in timber, but we only lose 2% of the stiffness. Cut that further, 130 millimeters, and we get 46% removed and only 70% loss of stiffness. So what happened if instead of C16 we use C24 for the flanges, and instead of the timber itself we change it with OSB, and you find that you get an increase of 46% in the stiffness over a standard C16 joist. And that's basically is the philosophy of an I-Joist. So there are different advantages when we're talking about I-Joist. The first one is optimized amount of material. As you can see, you can save a lot of material compared to a rectangular section. And that is important in an economy when timber is scarce. We are celebrating, and I'm very glad to see a lot of different projects with timber, but don't forget that it takes about 20 to 25 years to grow a tree. So optimize the resource as much as you can is paramount. Another advantage that timber I-Joist got is that they produce lighter. It weighs much less than other options. So create lighter structure. Hopefully it will save you some money for foundations. They are quick to install because people can handle them. Extremely stable because you got small sections, and also timber panels are very, very stable to moisture. They don't expand and they don't grow as much as timber does. And also you've got availability of deeper sections, longer spans, higher stiffness to weight ratio. And you can drill services. You only have to go through a 9mm OSB to drill a hole in order to pass electrical cable or a pipe. And that's a very, very usual scenario when you're talking about the traditional UK housing. And one of the features that I have seen in projects, especially Passivhaus projects, is that they are obviously very interested in the thermal bridging capacities of I-Joist. The fact that you have a very thin web that acts as an insulation, and you can put more insulation in the material. So if you want to go deeper, normally the projects I have seen, 245 deep, 300 deep, infill with insulation will give you very excellent, good thermal values that you can use to save money in heating. So just to finish, I would like to show some of the projects we have been involved. And as I said, these projects are more diversified now from typical floors to mezzanine floors in supermarkets or roofs or ground floors or even walls, as you can see there. I have attached some further information if you guys would like to have a look or learn more about engineered timber I-Joist. The first one is from the STA, is a timber frame datasheet. The other two from TRADA and Instructi. Finally, if you're looking for ideas of what you would like to see, what kind of stuff you can do with I-Joist, I have a link to the website in James Jones, where we describe typical projects that we have done over the years. Thank you, Robert.
Perfect. Thanks so much, Abel. Again, please pop your questions in the chat. Just a quick thing, Abel. There's the JGI software. Is that available on the James Jones website as well, right?
In the James Jones website, we've got an interactive span table, so you can go to our website and you can put your details to Eurocode 5, and you can get a specification for the I-beams. Software, we produce our own software, but they are released to our distributors. So, I mean, for this project, if you are at a stage that you need some reference calculator and you cannot find in the website, give me a call or send me an email. I'm glad to pass it through our software or to give you the resources you need to complete the project.
Perfect. That's great, Abel. That's very, very generous of you. And I'm sure if some of the those participating in the challenge decide to use I-Joist, I'm sure they'll be in touch with yourself.
Thank you.
Excellent. Okay, please hang around for the end as well, because I'm sure there'll be some questions popping up. And I'll just hand over to James now. James, please take hold of the screen. I'm looking forward to this presentation. Thanks, James.
Thank you so much, Robert. Can everyone hear me okay? Is everything working all right? Hopefully, yes. I'm slightly fascinated as to who is in the room in terms of, are you engineers, architects, quantity surveyors, building surveyors, contractors, acousticians? It'd be really useful just so that I can try and pitch what I'm going to say. If you could stick it in the chat, and I'll try and scan all 40 responses in very quick succession, just so that I can try and land this in roughly the right space. Okay, so we've got some architects, some engineers, some engineering architects, a civil engineer, building control, architect, engineer, construction management, post and beam designer and maker, building surveyor. Okay, fantastic. What a selection. So a little bit of everything. That is, it appears to me. I will do my best to try and appease all of you and to kind of hopefully cover a fair few bases. Let me click on the right tab. I'm actually going to do something slightly different. I don't have any PowerPoint slides. Instead, I have a visualizer and a stack of books, and I'm going to talk to you about some ideas. And I cheekily stuck my LinkedIn account at the top of my page, and I'm going to hopefully do some doodles. So I'm going to start by saying I'm in a very privileged position. Kelly introduced me really kindly and said I used to work in industry, and I did, and I used to design buildings, including lots of timber buildings, lots of concrete buildings. I worked on the Tate Modern extension for a little bit. I designed probably my least favorite project of all time was working on the roof of the Ferrari Experience in Abu Dhabi, which is a 1 kilometer across roof. It's huge. I hated it for so many reasons, but anyway, let's not dwell on that. Yes, so I've been an engineer for a long time, but for the last, now it's 7 years, I've been an academic. And the thing about being an academic is I can make suggestions and I can say things that maybe I couldn't say if I was in practice. And so I just wanted to start off with a little provocation. It took me a while to find this photo, but I don't know if you can see this, but it says aim low and miss. And this is actually a t-shirt I brought my brother-in-law about 15 years ago. That's not my brother-in-law, but it's a t-shirt I bought him 15 years ago. And as I've been thinking recently a lot about sustainable design, it's just a thought that has come back to me, that the diagram that we've been drawing around net zero, kind of the aim, and you'll see lots of different diagrams. One that I really like, which you'll find in lots of different publications, is kind of the carbon impact. And kind of we can if we start very early on in a project, we can have 100% impacts. And people call this, often build nothing, build clever, build smart, and we work our way down. And essentially that other diagram that Matt really kindly shared earlier, the kind of the A, B, C, D, E one, kind of essentially what we're saying is we're up here somewhere, actually GH, we're probably up here somewhere. And the aim is to kind of drive that down and maybe get to this line of zero. And the reason I say aim low and miss, and maybe me and Matt might have a debate over, we actually both live in Bath, so we might have a debate over a coffee about this in the future. But the reason I say aim low and miss is because actually our aim is to get to zero. Now that used to be a fairly positive aim, but unfortunately we've used up so much of our carbon budget that actually is not a particularly great aim now. And the problem is that is our aim and we're missing it. Essentially we're trying to get to zero, but actually we're not even anywhere near it, frankly. So that's my provocation. That's kind of where I started off. So I wanted to talk to you about some ideas, and I was going to just start by mentioning this book just because I finished reading it. I think reading books is super important for a variety of reasons, but it really helps to stimulate your imagination, your thought processes. So from what is to what if. And I actually and Tabitha I think has the link. I actually recently wrote a book on the conceptual design of buildings. It's aimed at structural engineers. If you're a student and you're doing a final year design project or an earlier year's design project, this book is, I think, hopefully gold. But if you're an architect, I think there's still loads of stuff in here, and it's based on not just my experience, but a whole load of us. We wrote it together, and there's a whole load of experience put in here. Please don't buy it, but ask your library to buy it, or hopefully if your university uses the construction information services, then hopefully you can download it for free from there, because it's an iStruct book. Anyway, so questions I think we should be asking. So I've got a whole load of what if questions. What if cement is banned by 2030? What if energy intensive materials are taxed so they cost 10 times more than they do now? What if your project was the last project to use this particular material? What if all metals had to be recycled? What if our timber usage is limited to guarantee the world's forest is growing? Which I think is a really important question, and kind of does relate a little bit to what Matt was saying earlier about it's all very well to talk about carbon sequestration, but you can't kind of rely on what's going to happen in the future in what we're doing in the now. So I actually took a what if question, and I think those what if questions are really powerful. I took a what if question recently, and I actually drafted a little article that the I-Struct asked me to write an article for them. This is available for, well, I was going to say for free. It's not free. It's free if you're a member of the I-Struct, which I'm not, even though I think they're fantastic, but I don't want to do the big scary exam. I'm sure some of the people on the call are. But I think if you're a student, you should be able to become a student member. Definitely if you're an engineer, I would have thought you could become a student member regardless of what you're studying. They've got loads of fantastic resources. If you're a student member, then all of the articles that they've done around net zero and all of that stuff you can get for free. So I'd really recommend you dig out not just this article, but look at all the different stuff. I noticed in the chat earlier, someone was asking about sustainable design and resources. I mean, they've got an absolutely incredible wealth of great resources on the I-Struct website at the moment. So I started by asking, what if carbon drives our design from the outset? And I was trying to get to, so this is a diagram that Matt drew, I stole the one from BuroHappold. I've got lots of friends with BuroHappold, but I redrew it by hand to make it look a little bit more squiggly. And I said, what happens if we start and aim for down here? So rather than saying, oh, okay, I'm going to design a building, it'll probably be at least 300, 350. What happens if we say, I'm absolutely not happy with that position. I'm going to try and get as close to zero as I can. And I'm going to try and make as many decisions as possible to help me to stay down here, rather than assuming a whole load of other things. And we could start to ask some what if questions. So we could ask about the load. Is the load suitable? Could I reduce it? Are the spans suitable? How could I make the spans short enough that I'm definitely down here? Is the deflection requirements, are they suitable? One of the big things that can drive design is the deflection requirements for facades. What if we said, actually, I'm not going to change my structural design to fit a facade. I think the facade should match my structural design. What an interesting question. Sometimes we have no control, right? So if you're designing a hospital and you've got to design for vibration, then I think there's a question and we can assess it and we can go, okay, well, I think this is really important. It's important we design for vibration for a hospital or for a laboratory or something like that. So actually, maybe I can't use the lowest carbon solution. Maybe I have to increase it. But we start to realize that actually these decisions we make, more load, bigger, lower, more, tighter deflection criteria, all of that stuff, actually all of those things drive up the carbon in our project. And so if we start making those decisions and realizing that we're making decisions that are driving up the carbon, that is really, really interesting. So I've got another what if question for you. And Robert will be able to correct me. But what if the timber for this project were all locally sourced? What if we started by, rather than saying, this is the load I need, and these are the spans I need, and this is the kind of the dimensions. What happens if we started the other way around? This is the material we've got. This is what we've got available. And we could use like Matt's idea about taking big bits of timber and chopping them up and making smaller things and sticking them together. And that would be excellent. And we could look at like the timber I-Joist idea and actually say, oh, fantastic. Like a lot of timber design is governed by stiffness, it's governed by deflection. But what if we, kind of used our material, therefore, to be more efficient? But what if that timber was locally sourced? And actually, I've sent Tabitha a few links, and now is a good time to mention a few. So one is ModCell. So I used to work for a company called Integral Engineering Design, and two of the directors for Integral were also directors of ModCell. And ModCell, certainly for a while, and I'm not quite sure where the company is at the moment and whether they're still operating, but for a while they did this really interesting idea where rather than manufacture their prefabricated straw bale modular construction panels in a big factory, they used what's called a flying factory. So they resourced or sourced all of the materials as locally as possible. They then created a factory as near to the site as possible, where they then created their prefabricated panels, and then they delivered them to the final site. And so they ended up with really fascinating projects like Hayesfield. I think we could argue, I could argue, Hayesfield is probably one of the most sustainable, if not the most sustainable building. It's in the entire UK. Hayesfield is a straw bale timber frame building. It's a science block for a girls' school in Bath, and it's a really interesting project. So what if we were to do something like that? And you might be thinking, well, that's just not possible. That sort of thing is not possible. But actually, another project which Integral worked on is a project called Cody Brennan, which is in Wales, and they source local timber, and they turned that local timber into a particular type of construction, which is called Brestipole. So you may have heard about CLT, which stands for cross-laminated timber. Well, Brestipole is a form of ULT, Unilam, you know, there's a few different words. I think we debated when we wrote some books about what we should call it. I think we ended up on ULT because some of the others might be trademarked. But essentially, it's a form of Unilam or single directional timber. So you basically put a whole load of joists together. And then what you do is you put hardwood stakes through the middle, and those hardwood stakes have a different moisture content, and as the two change dimensions, they lock together. There's no glue, but they lock together, and you end up with solid timber panels. And this was done using local Welsh timber in Wales, which means there's precedent for doing this. So what if we were to take that approach? And I can't remember why I even included this book. I'm just reading it right now, and it's great. I would recommend it. Really interesting. Anyway, regenerative design thinking, that will come about later. So what if we did that? And you might be like saying, well, I don't know what grade the timber would be. And if you don't understand what grades are, don't panic. They're something that engineers like to use to basically conglomerate all these different things about a material and say, actually, what I want to know is what grade is it? So I don't really worry about what species it is. I could design a timber beam and it could be made out of spruce or pine. Actually, I'm worried about how strong is it? So as a structural engineer, that's my question. So I will grade it, and that grade will tell me how strong it is. And the grading process is complicated, and it covers a whole load of things. It's not just the species. It's to do with things like the knots and damage, and there's all sorts of different things that go on in that. And if you'd like to know about that sort of stuff, then I actually wrote this book, Designing Timber Structures, to explain all about that. Oh, I was looking for that. That's about shear deflections. That's useful for my students. Excellent. Okay, so and there's loads of stuff in here about properties of timbers and grading and all of that sort of stuff. But I would almost take a step back, and actually I'd really encourage you to read this chapter and think, okay, rather than thinking about grade, maybe I should flip the question around the other way and say, what timber is available, and what sort of species is it going to be, and how long is it going to be growing for? Is it going to be quick growing, slow growing? What impact will that have on the strength? And all of those kind of questions, and maybe try and think about it that way around instead. And hopefully you'll end up being able to say my timber is, and what happens if your timber isn't any of these grades? What happens if it falls off the chart? Well, number one, there's much better charts that are in British standards, and you can hopefully find those if you're at university or work for a company. Hopefully you have access to BSI online, so you can just look them up and find out what grade you might use. And then you can start to design with that grade. So I was encouraged to talk about solid timber. And where might I design? So some what if questions. So what if we use local timber? What if I was to start with that? What if I started to say, I know what timber I've got, and let's say, just for the sake of argument, it's C12. What questions could I ask? How far could it span? And at the same time, how much load? Because the two things are not separate, they tie together. We could start to ask these kind of questions. And actually, these are exactly the questions I started to ask myself when I wrote this book, Structural Timber Elements, which my friend Simon Smith, he worked with me at Ramboll. And when I left Ramboll, well, when I left Integral to become a full-time academic, he emailed me and said, I think it's really important that there's this book. It's a pre-scheme design guide. It basically rivals the Economic Concrete Frame Guide, which is another very good book if you want to do pre-scheme design of concrete frames. And so he said, what if you know, now you've got all this spare time because you're an academic and you clearly just sit around all day twiddling your thumbs. What if you were to write this book? So I said, yeah, why not? I'll give it a crack. And so I started to look at what span could I achieve with different sizes of timber. So rather than saying, I've got a load and it's got to go this far, what size timber do I need? I said, I've got a timber and it's got this load, how far can it go? And that process is actually fairly straightforward. It's not difficult. I created some spreadsheets. I created some big spreadsheets because I looked at a lot of different options, not just the ones that are presented in here. I included a lot more, and I left some out. But I asked those questions, and you could do the same thing. So you could find out what is available locally. How could I make it? What could I make with it? Could I make I-Joist? Could I make the equivalent of glulam or LVL? What could I do? And then ask, you know, for that material, how far could it go? How much load could it take? And then could I make my design work to those constraints? So kind of taking the whole thing in the opposite direction. And to do that, you might go, well, actually, oh gosh, I don't really know how to design timber, and I've never really done that before. So don't panic, because the whole idea is that this book will take you through every single bit of the process. So this is designing timber structures, and it will take you through literally every bit of the process. It will tell you how to design a joist. It will explain what it is. It will talk about factors of safety and probability and uncertainty, which I think is another great what if question for another day. It will tell you how to calculate your actions, your permanent action, which is the weight of the floor, the weight of the ceiling, and all of that stuff. Really important things to know. The variable action, the weight of people and stuff, and all of that sort of stuff. If you can't find the situation you're looking for, look in chapter 3. There are more loading diagrams in there. And then how to analyze your joist. So these are the shear force suspender moments, as we saw in the last presentation. How to design for this stuff. How to think about long-term creep, displacement, all of that sort of stuff. And at the end of the whole process, you end up saying, okay, and this is how I design a beam. And we can then crack on and design it. Now, if it just so happens that that beam isn't in any of the design tables, well, that's okay. There is ways of finding out that information. So I think I'm done. I hope that's okay. And I'm really looking forward to your questions at the end of this.
Brilliant. Thanks very much. I think I thought I really liked the almost the provocation, James, of what if you use local timber? So what if we actually turned on its head rather than, you know, starting off with a building and then trying to, you know, figure out what timber to use. Let's start off with the timber and figure out how to make sense of that relative to the actual building. So that's certainly food for thought for the challenge. We'll save other questions and hopefully conversation at the end, but thank you very much. I'm going to hand over to Beth straight away. And it's good to see you again, Beth, since the last met in Hereford when we did some work with the Edinburgh Napier students, which actually was a forerunner for the design comp. So it's good to see you again, but I'll hand over straight away and look forward to your presentation.
Cool. Just share my screen. Hopefully you can see that and not notes, not that there are many notes, but hopefully you can see the full screen. Cool. So yeah, Kelly introduced me, but yeah, so I'm a certified Passivhaus designer and structural engineer with a background in architectural design as well. And yeah, now there's 3 structural engineers and certified Passivhaus designers in the UK. So I'm really pleased that the other 2 have joined. A couple of other engineers passed at the start of this year. So yeah, now one of 3 rather than the lone one. These are some of the projects that I work on. I do sort of done a range of stuff since graduating, but now do a lot of domestic one-off houses and extensions and weird things like staircases and then canopies for RHS gardens and all sorts of things, but focusing on timber frame passive houses and low energy house design for the most part, and some of those projects are up here as well. And then I'm just going to today I'll talk through some typical passive house details or low energy timber frame details, and particularly using I-Joist construction for that context. And then I'll talk through an example project and I don't have time to go through Passivhaus in detail today, but I think you're going to get a load of other presentations on what that actually is as the standard. So I'm just going to sort of assume that we are talking some of the same language to start with, and hopefully you'll get some catch-up talks on that at some point. Yeah, so I'll talk you through. So a lot of the projects that were on the initial slide are based on the sort of this kind of system. It's not like a system you buy off the shelf, but this approach, I guess. So we're looking at using engineered I-Joist frame. A lot of these are James Jones frames as well, rather than any other manufacturer. So using an engineered I-Joist frame, using the same depth of I-Joist for the walls, the floors, and the roof, ideally, and the same flange width. That just makes buildability easier. You can the builders can buy the same size timber and then just use it anywhere. They can use offcuts anywhere. There's noggins and all that kind of stuff. Just makes it really straightforward. And then on the internal face, we're looking at doing the air tightness on the internal face of the timber frame, and that in most cases is a pro-passive OSB board. That's a OSB board that's basically like lined with more plastic and more glue than you would usually get on an OSB board, and that's that then forms the racking board as well, and then it's also the vapor control layer to stop excess moisture getting into the construction fabric. And then between those walls, those I-joists, whether they're wall studs or floor studs or roof joists, we've got 300, well, a depth of blown cellulose insulation. A lot of the projects I'm working on are using warm cell, which is a blown recycled cellulose, recycled paper insulation, but others are available. I'll talk a little bit about that later. And then on the external face, we're looking at using a rigid sarking board. So panel vent, or there are other manufacturers that do a similar board now. So that is then a breathable board. So this is called a breathable timber frame construction, which is the easiest way to avoid any kind of future issues with moisture buildup and within the building fabric, where you can't see it and where it can cause problems down the line. So yeah, so breathable fabric, and that's the idea then, is that your internal layer is much less breathable and lets much less water out than the external layer. So your moisture path is generally out towards the external face. There's better explanations of that online elsewhere, people who know lots more about moisture movement through construction fabrics, but that's a really basic introduction. And then we are, so we're in, and then we're using different forms of construction. So a lot of the projects I'm working on are sort of a hybrid of balloon frame and platform frame construction. So balloon frame being that the wall studs continue up all the way from sole plate to eaves level in one continuous run, which is obviously achievable with engineered timber, which you wouldn't be able to do in a stick built softwood timber frame. But then that does also then cause issues with buildability in terms of temporary works. In order to have that length of timber stuck up in the air, you need some kind of temporary propping, which working with domestic builders is often not considered or sort of taken into account ahead of time. So a lot of the domestic builders I'm working on now, we build the I-studs up past the floor zone, rather than platform frame being the floor zone built on the wall zone, the wall studs. So we build it up past the wall studs, and I'll explain that a little bit when we get into some of the details later. And then fixing the floor onto the side of the wall studs. So we're sort of doing the two so that they don't have quite the same level of temporary works required, but they're able to make air tightness and things detailing easier, which I'll explain in the next detail because it will make more sense. And then we're obviously talking about timber here today, but all this timber frame superstructure is then generally sat on a insulated raft foundation, because this makes then the thermal bridging detailing easier and the air tightness bridging detailing easier. And then also things like holding down of timber frames, which is a big consideration when you start looking into yeah, any kind of level of scale of timber frame structure. They're lightweight structures in the scale of things. So how do we hold them down and make sure they stay there when wind loads particularly are applied to a building? So I'll talk through this detail that's on the screen now. So this is generally a wall to foundation detail, and we're looking at the insulated raft foundation there, which is sort of green with the pink around the outside, and we've got the wall studs sat on it. So you can see there that the wall studs sit partially on the raft slab and partially overhanging the insulation. That's a way to improve the thermal bridging detailing, that you could sit the wall studs completely on the foundation, but then you've got this sort of weird junction of how you bring the insulation up past the raft slab and then join it onto the wall studs without forming a weird little shelf. So the way that most people are doing this, particularly for passive house projects, is to sort of squidge those wall studs out over the insulation so that you can get some level of insulation around the edge of the slab, and then you've got the same thickness of insulation basically coming underneath your slab up the side and then joining onto the wall insulation. So then that's sat on like a little timber sole plate, and then onto the raft foundation. You probably will see details of raft foundations with edge thickening details. So the sort of a zone at the edge of the slab is thicker than the rest of the slab. That does help in terms of concrete usage, and it's suitable in a lot of situations, but particularly the work I do working with domestic builders, they're not generally concrete specialists. So keeping the raft slab simple in terms of, we can just stick down a layer of mesh, we can stick down some U-bars at the edge, and we can stick down another layer of mesh. It generally makes it easier to build overall, whilst you are technically using slightly more concrete than you maybe necessarily need. Yeah, and then that's all sat on then the ground. You'll notice that the raft level is set that 150 mil above the ground level, so that we're keeping our timber away from the rising damp or splashes and that kind of thing. And then that means that you don't have any below ground block work to bridge that junction between your foundations and your timber frame. And then this, moving on up the building, this is then a standard connection of a floor into a wall. What we've got here is the wall studs, like I say, running past the floor joists. We then bring a timber bearer that then fixes onto the wall studs ahead of time, to then fix our floor joists onto that. Then to do the air tightness past that, you can either run the OSB board continuous past the wall bearer, but sometimes that is tricky to build. So another option is to run a strip of air tightness membrane behind that wall bearer to then tape onto your two wall boards either side. Like I said, the way to break that junction to make it sort of platform build is to then bring that wall stud up, and we generally bring it about 100 mil above the level of the floor zone, because that then gives a easy junction above the floor to then do the air tightness taping and make sure we're getting a good air tightness junction across that floor junction. And then moving on up to the eaves junction, this is what a lot of our eaves junctions are ending up looking like. So we've got our eaves beam, a big LVL, in most cases laminated veneer lumber, could be glulam, depending on the availability and the sizes of glulam. So some kind of engineered timber, because then it can be long and straight across the whole run of the eaves of the building. And then our rafters then fix onto the wall, to that eaves beam, and then that eaves beam also provides our lintels of any windows we've got up near the eaves. And then we've got because when we're dealing with blown insulation, we're always thinking about getting big long boxes that we can blow our insulation into. So usually your wall studs would come up and they would break it, and then you'd end up with lots of little pockets of insulation along the eaves, which just is a recipe for things going wrong. So what we've done in this case is we made our box along the length of the eaves of the building, so that we've got, again, a nice run of insulation to go all the way along the eaves. And then moving on further up, the ridge junction is pretty much the same as sort of standard timber ridge junction. This is the diagram here has got an offset ridge beam, but you could have a central ridge beam, and then you've just got the rafters connected across the top of the ridge. And then again, similar considerations when you're looking at the air tightness requirements for passive house is that you generally need a strip of air tightness membrane across that ridge beam before you put the rafters on, so that then you've got something to make your air tightness line continuous over the ridge. So I thought then we'll just quickly go through an example project that I've done. Here is a little passive house here. It's a 1.5 story passive house. So when you come to look at passive house in more detail, you'll hear about form factor being a big consideration in making passive house sort of achievable and affordable and easy to do. This bungalow is bad for form factor. It's got a lot of external envelope for the floor area you're getting. So this one, this project has 400 deep I-joists as the walls on the roof. And then it's got a sort of partial suspended floor, and you'll see in a second. And those are at 300 deep. So we did swap the size of I-joists around in this project. Yeah. So the architect and the energy advisor wanted to do this project without a ridge beam. They were thinking of it saving costs without that ridge beam. I'm not actually sure that it did, because it then required a lot more temporary propping before they could get the structure up and self-supporting. But there we go, we made it work, which worked really well in this case, and with using I-joists as the wall studs, because then we've got some bending capacity in the wall studs that we wouldn't necessarily usually have, particularly not if you're comparing it to a masonry wall. So what we could do is use that bending capacity in the wall studs as a big frame there, and we're using the floor joists then to tie across roughly at eaves level. They were in this case roughly at eaves level. And then we're forming a big frame truss there at the top, and using the bending capacity of the I-joist to do that little offset of the tie not being quite at eaves level to then tie the roof structure. And it looks very nice. So they've got a little bit of floor there, and then they had a little bit of a double height space, which I used a slightly different approach to the roof tying there, but sort of similar idea. This site also, varying off the topic of timber design, but had differential ground conditions. So on one side of this building, there was a very hard limestone bedrock, about 300 mil below ground level. And then on the other side of the building, there was that limestone bedrock sort of dipped very, very sharply. And then there was a weaker stone at then about 2.5 to 3 meters deep. So we looked at some various different foundation options here. We looked at designing the raft for the differential settlement and all sorts of different ideas. But in the end, we decided to go with a strip foundation underneath the raft. That then kept the raft depth shallow and meant that we could then use a concrete that had a lower embodied carbon for the mass concrete strip foundation. So this is a sort of eaves detail, a sole plate foundation detail, slightly different to that initial detail that I showed you, and what we ended up there for this project. And then that's what it looked like in the end. And for some references, I will send around these slides, but some references for people to follow, groups to look at for more information on passive house and low energy design and all those kind of things, different products to use that are low carbon and low energy on the screen. There you go. I'll leave that up for a second and people can take notes, but I will send it around.
Yeah, that's great. Thank you very much, Beth. And it's really interesting, isn't it? You know, in terms of as we move to higher performance thermal envelopes, you know, the use of I-joist, because essentially they can give you that depth of section, and then you can fill it with wood fibre, and as much as cold bridging is reduced when you're using timber as opposed to something like gauge steel, etc. I'm sure that the use of an I-joist improves that benefit again, right? Because of the reduction in section.
Yeah, and like Abel was saying, that we want to be reducing, and the others have been saying that we want to be reducing just material usage generally and using it efficiently, which this helps to do. It's one way of using timber really efficiently.
Perfect.
I'll stop sharing that now. We can see people's faces.
Excellent. Yeah, I'll invite everyone back, and please feel free, even if you've not spoken yet this evening, to turn your camera on if you're one of those that are participating within the competition. We'd love to see from you, hear from you, etc. There is a question in there from Oisin to yourself, Beth. With the new build passive house, details are using both OSB and sacking boards for shear resistance. Do you see that comment in the chat? Do you want to pick up on that one?
Yeah, in most cases, no. Some people don't want to put the the panel vent on the outside because it is more costly than a breather membrane, but it does give other benefits in terms of like, yeah, stiffness. But yeah, so a mixture. It doesn't actually tend to add that much in terms of the racking resistance of the panel to add a second board, in far as I can see. So yeah, trying not to if possible.
Perfect. I'll perhaps bring Kelly in a moment just to maybe share her thoughts. But just before I do, I mean, just to give her a forewarning, right? Just that, do you have a, with the I-Joist systems that you're using, Beth, because, you know, Abel, there's the JGIs, which is solid section. There's obviously, you know, you can have an engineering section for the flange. There are alternatives even in terms of web materials, etc. Is there a preference that you have, or is it yeah, any particular thoughts without offending Abel perhaps, but yeah. But do you have any, or are they, do you find they're all suitable for the use, or any?
Yeah, personally, I don't find I know I'm going to offend some manufacturers here, but I don't find the LVL flanges to give that much benefit in terms of the scale of things that I'm using. Yeah, and also I like the idea of being able to use particularly lower grade timber and locally sourced timber, although that's something maybe Abel can hopefully develop in the future, but using UK grown timber for these products as well. So using solid timber is a good, yeah.
Yeah, that's something that obviously the James Jones group have a lot of sawmills, and we cut homegrown timber. And I always got my bosses on the main office with a very long face asking me, when is it that you're going to take some of my wood in the sawmills and produce an I-Joist? And I always said, hey, like, I would love to do it. And actually for timber walls, it's feasible because the actual capacity for C16 timber is more than enough for what you need for those projects. So I really, really would love. In fact, in the past, what I have done trials already using our sawmill flange material and see how that goes through the process and see. But the only thing is you have to do a lot of fine tuning, but as everything in life, if there is a demand, there is a way.
Yeah, that's good to hear, Abel. But we do have a question from the audience, so you can hold fire just now, Kelly. So we'll take the question from Ali, if you're there, Ali.
Hiya. Thank you all for your presentations. That was really fun to watch. I'm a graduate from in architecture. I just had a really simple. Actually, I have two questions, but they're really quick. One, I think for Beth, but I think anyone could answer. It's just a very simple question, but I just never quite got an answer in my studies. It's about using rigid insulation around the floor slab, and it goes into the ground, and it just surprises me that it doesn't need any protection. So EPS and things, you don't need to worry about the damp coming from the ground, from the soil.
They're pretty inert, to be honest. It's generally advised to use XPS below DPC level, but I like it, like you saw, there are people using EPS, so you do have to be careful of the long-term creep when designing them, which is something that often gets missed, particularly in terms of the grade, the strength grades that you get given by manufacturers. Those sort of values that they give you are quite significantly reduced when you look at the sort of long-term creep of the material. But yeah, it's been used on the continent quite a lot. If you luckily they've translated a lot of the information now from German, but when I first started designing these, you had to translate it using various German information. So they've got a lot more experience with it, often using like basements and ICF basements and that kind of thing. So if you want more information, that would be the way I would send you sort of examples in Germany and on the continent.
Thank you. And if I can, just one more, I think for Abdel, this is something I wish I knew more about, but I'm just thinking off the top, if you're using two different materials in the I-Joists that have different properties, of course, the OSB and then the C grade. Does that complicate when you're, for example, considering structural calculations that for typical distributed point loads, that you're using composite materials at any point during the typical, for example, trying to use them for a standard load in a room? Because I don't understand, I didn't graduate in engineering, but I'm just imagining that you have to take an extra steps to account for the fact you're using two materials. Is that the case?
That, Ali, that's a very good question. And that's why basically we had our design office in the process when we started producing I-Joists. We developed the design of I-Joist parallel to it, because and I-Joists have been more complicated section to design. But there are, I mean, I was going to say shortcuts. There are models that make your calculation easier. For example, when you're talking about bending stress or bending strength calculations, you can see an I-Joist like if you have to do with bending stress, the flanges provided. So you calculate it as if the flanges are alone. If you have to do shear calculation, the OSB is the one providing the shear. And when you go into deflection, you've got two components always. You got a bending deflection and a shear deflection. So you consider the flange material for bending deflection, the OSB for shear deflections. So doing that kind of simplification on the model does not give you, well, it gives you minimal error to the more complicated solution that is probably unapplicable, and is probably what every single I-Joist manufacturer is applying in the country. So using that kind of rationale, you can simplify design. Yeah.
Thank you very much.
Great, thank you, Abel, and thanks, Ali, for the questions. All good. I think we're actually over time now, so I don't want to hold everyone on for very much longer. But I think I'll just pass it back to yourself, Kelly, just for any closing comments, any thoughts that you want to provide, and then Tabitha and I are more than happy to kind of hold on to speak to anybody that's looking at team building or any questions, etc. But I'll hand it to yourself, Kelly, and then let you guys get on with your evening.
Thanks, Laura, and thanks everyone for your talks. I thought it was, I learned something every one of them, so thank you very much for that. I thought I'd just finish on the question I popped in the chat, which James and Matt have kindly answered. But what if you were the client? What would be your #1 priority in the brief for your own house? What do you think, everybody? Perhaps while Abel and Beth have a think, James and Matt can recap on what they said in the chat.
Matt, do you want to go first? You put your answer in first.
Yeah, sure. It's probably worth saying. I think I'd be a real pain in the neck as a client, actually. I think all of us in the room here, I think we'd all be, it's bad enough if you have a plumber come round and sort of poking in and asking them what they're doing and why they're doing it. I don't know, there's lots of requirements that you'd need kind of spatially in terms of the way you live and everything. But yeah, I would definitely be looking to push it to a lot of the themes that we've talked about this evening. But I'd be perfectly prepared to sacrifice the amount of space that I had or the amount of storage that I could sort of put junk in. And, you know, I wouldn't be expecting to get everything, not for nothing, but, you know, I'd be quite prepared to be told you can have this that's high up on your list, but you'd have to sacrifice this which is lower down on the list. And I think I would be challenging the designer in that way, and getting them to challenge me as well.
Cool.
Thank you. Yeah, I mean that's what we're looking from our clients, isn't it? When we're saying have smaller spans and use different facade materials. So it's nice to see that you're already on board with. James, you want to? I liked your answer a lot. It's very much what I'm trying to do at the moment. So.
Great. Yeah, my idea was to reuse my existing house. I've only lived here 20 years, so I feel like it's definitely got a lot more mileage to go, right? We built an extension about 13, 14 years ago, and it's a very, very boring masonry extension with timber joists. And I do regret not building it out of timber, looking back. And actually, I've been doing some digging around, and I'm reading a book by Brené Brown. I don't know if you can read that, but it says the idea of no regrets doesn't mean living with courage. It means living without reflection. To live without regret is to believe we have nothing to learn, no amends to make, and no opportunity to be braver with our lives, which I really love, because as engineers, I think we often have done things in the past, which maybe we think, I wish I hadn't done that, or I wish I hadn't worked on that, or actually I understand now a lot more about this than I did 10 years ago. And in the light of that information, maybe I would have done this differently. And actually, if we accept that and say, oh, okay, if I was to do this again, I would do it differently. I think that's actually really powerful. So rather than I'd stick with my house, and I'm not going to knock down my masonry extension just to replace with timber. That would be ridiculous. But I wish I had done it out of timber in the first place.
Completely agree with that. Thank you so much, James. And I think that's the joy of being perhaps a student right now, is that you've got your whole career ahead of you, and hopefully you're doing design competitions like this and listening to speakers like we've had today, and therefore won't make as many regrettable decisions as we have in our careers. Okay, Beth and Abel, have you got any thoughts on it?
I guess mine would probably be an extension of James's, because I'm in the process of slowly retrofitting my house, which is interesting, and definitely, like James has learned a lot. There would be definitely things I would do differently. Probably one of the main ones would have been, because I installed a new gas boiler five years ago now, and I probably would have maybe hold off a little bit and tried to do an air source heat pump. Would probably be what I would be looking at. But yeah, I think probably thinking that you don't need to do everything in one go. Sort of planning stuff needs to be done beforehand, but yeah, I sort of say to clients a lot, well, you could start with this and then see how you get on with it, and then maybe if you're desperate for that log burner 2 years in, when you can put it in your passive house and spend your extra 15 grand on whatever it is to light it twice a year. But you could, so it's like that, sit with it and do things in stages.
Learn from your building, and design as you go. I like that. We should be learning as we live in buildings, definitely. Abel, sorry to put you on the spot. Do you have an answer?
I was going to say, I just moved to my house a few years ago, so I better don't. I really am a fan of passive house. What I would like for my house, and probably being selfish, I don't want to pay bills. I want a place where it is comfortable to live inside, and it can basically self-stay with my head.
I think that's the dream for us all, isn't it? Great answer.
The only problem is that I will probably become so obsessed with how the floor moves and how it vibrates that I think my wife will throw me out of the house just with my obsession. I think the future of, I mean, we have seen it at the moment, how energy bills are rising, and that's something that we're going to have to confront in the future.
Completely, yeah, great. Robert, have you any thoughts? What have you been the client?
Well, I have to be an interesting circumstance where I have a client at the moment, I guess, because I'm extending onto my house using technologies we've researched, which has proven interesting. So we've we've got it up, and we're just getting it clad, so it's got it's mass tip. So we've used locally sourced homegrown CLT and nail lam and glue lam. It's a 45 meters squared in total, so it'll be an extension to another extension to our existing 1950s bungalow. So I guess what Beth's saying, we've done a bit, done another bit, and learning as we go. So I think the thing I would probably want at the moment is to have noticed that because we're doing it, we're having to put zinc cladding on it to get because of planning, etc. On the roof, but as part of the quote, they hadn't actually included something. So now I'm getting hit with another bill. So as a client, I think as a client, it's maybe having more attention to detail at the very start to know that everything's absolutely included, because you think it's all there and then it comes to that bit's been missed, and you're having to figure out why it's not being included. So yeah, that would be my bone of contention for today, sitting here as a client to check more thoroughly the quotation from the roofing company.
It sounds like you've really taken the homegrown and local on board, though. That's nice to see. That's part of your brief. So I hope that is something we all think about in future as well. Well, thank you, everybody. I know we're over 16 minutes over. Sorry about that. But yeah, I'll let Robert and Tabitha finish off the session if any of the students got any questions about the competition. And thank you to all of our speakers. Thank you very much.
Thanks all.
Cheers all. And thanks to all the speakers. Have a good night. And Tabitha and I will